Welcome to this, the second video for Maths and Stats 2. In this video we've got two short exercises to go through, and in the first exercise we are asked about the unbiasness and the consistency of the OLS estimator. But the twist on what we have compared with what we had in lectures is that this is the OLS estimator where we're constraining that the intercept is equal to 0. So just to emphasize what that will look like, our data is generated, or at least we're assuming that the data is generated using this data generating process. Yi is equal to beta xi plus ui. The intercept is set equal to 0, so we are estimating a line. Our fitted line goes through the data from the intercept looking like that. So that might be our estimated line using OLS. And we're using this estimator because we have some economic belief that the line should pass through the intercept. So let's start analysing this estimator. So the estimator that we're dealing with here is given in the question. Beta hat is equal to the sum of the xy's over the sum of the x squared. So let's write that out in full. And whenever we're trying to assess whether or not an estimator is unbiased or not, usually it's best to start off by substituting in the data generating process. And we're told the data generating process here, yi is equal to beta xi plus ui. Well, we're assuming that this is the true data generating process. So from all of this, we're going to assume that this is how our data was actually generated. So we've defined the model correctly. So let's substitute in our data generating process into our estimator. So we can rewrite our estimator, substituting in yi is equal to beta xi plus ui, and we get something looking like this. We've got the sum of the beta xi plus ui multiplied by xi over the sum of the x squared. Now, with this summation on the numerator, we can just multiply out the brackets. We've got beta xi times by xi, so that's beta xi squared plus ui xi. Because it's a summation, we can split this into two summations, so we can have the sum of the beta xi squared plus the sum of the ui xi's. So we can rewrite this as being beta times by the sum of the x squared plus the sum of the x u's all over the sum of the x squared. And since we've got all of this over a common denominator, we can split it into two fractions. We can have the sum of the x squareds over the sum of the x squareds and the sum of the x's over the sum of the x squareds. So we end up with this is equal to beta times by the sum of the x squared all over the sum of the x squared plus the sum of the x u's over the sum of the x squared. Now, obviously, we've got sum of x squared over the sum of the x squared. So that just is equal to 1. So we end up with this is equal to beta plus some stuff. So it's the sum of the x u's over the sum of the x squared. Now, you'll notice that I've been changing my subscripts from the previous line to here. We've got I and j here before we had k and l. All the subscripts mean is it's tying these observations of x to this summation. So this xi ui means that it's belonging to that summation. The key thing here is that the range that they go from is between 1 and n each time. So far we've managed to rewrite our OLS estimator as this. We've not yet proven anything about this. All that we've done is we've assumed that the data generating process is yi is equal to beta xi plus ui, and we've been able to rewrite our estimator like this. Now, in order to prove that an estimator is unbiased or not, we need to take expectations. Remember, an estimator is unbiased if the expectation of the estimator is equal to the true population parameter that we're trying to estimate. So in this case, it would be unbiased if the expectation of beta hat is equal to beta. So we take the expectations of beta hat, which is going to be the expectation of all of this, the expectation of beta plus the sum of the xu's over the sum of the x squared. Because of the rules of expectation, remember the expectation of a sum is equal to the sum of the expectations, this is going to be equal to the expectation of beta plus the expectation of this fraction. But remember, the beta is just a constant, the expectation of any constant is just a constant, so we're going to have this is equal to beta plus the expectation of the sum of xu over the sum of the x squared. Now, in order to analyze this last bit, in order to analyze this expectation here, we need to look at our other assumption. Now remember, at the beginning we assumed that the conditional expectation of the error terms, the ui terms, given any particular value of the x, was equal to 0. So in order to analyze this, we're going to use our assumption, but we're also going to have to use the law of iterated expectations to find the expectation of this term. So this whole expression is going to be equal to beta plus the expectation over all possible values of x of the conditional expectation of the sum of the xi ui's over the sum of the x squared given a particular value of x. So how does this help us? Well, if we're given a particular value of x, we can treat the xi's and the sum of the x squared as fixed. We can take them outside of the conditional expectation. The only thing that will be left in the conditional expectation is the ui term. So we'll end up with this being equal to beta plus the expectation over all x of the sum of the xi's times by the expectation of u given x all over the sum of the x squared but we know from our assumption that the expectation of u given x is equal to 0, so therefore we can rewrite this as being equal to beta plus the expectation over all x. Now what we have here is we've got the expectation of ui given x, which is always equal to 0, times by xi, so we'll have the sum of xi times by 0 divided by this sum of the x squared, so we have x times by 0, and we add up all of those cases, so we'll have 0 in here. So this is just going to be the expectation over all x of 0. And this is only because the expectation of u given x is equal to 0. So provided our assumptions are correct, provided we've correctly defined our regression specification, so we've correctly defined the data generating process, and our conditional expectation of the u given the x is equal to 0, then we have an unbiased estimator. The expected value of beta hat is equal to the true population parameter. Now, moving into our second part of the question, we're asked to show that this is a consistent estimator. And remember, in order for it to be a consistent estimator, the estimator needs to converge with probability towards the true population parameter. Now, we showed in the previous part that once we substitute in our data generating process, provided that data generating process is correctly defined, we can rewrite our estimator as beta plus the sum of the UIXI over the sum of the x squared. Now, a trick that we'll often use when trying to prove that an estimator is consistent is we will try and convert something in here to be related to a sample mean. So we can rewrite this as being beta plus 1 over n times by the sum from I is equal to 1 to n of ui xi over 1 over n times by the sum of the x squared. Now, why do we do this? Well, we do this because when we're looking at p-lims, we're looking at the probability limit. The weak law of large numbers tells us that the probability limit, the p-lim of any sample mean, is equal to the expected value. So if an estimator is consistent, the p-lim of the estimator is equal to the true population parameter. And remember, the p-lim is looking at the probability limit of the estimator. It's looking at what happens to the estimator as the sample size gets very, very large. Does it converge in probability towards the true population parameter? So we have our beta hat, which is beta plus 1 over n times by the sum of the UIXI's over 1 over n times by the sum of the x squared. So our p-lim of beta hat is equal to the p-lim of beta plus 1 over n times by the sum of the UIXI's over the sum of the x squareds. And remember, we have various rules relating to the p-lims. First rule is that the p-lim of a sum is just equal to the sum of the p-lims, and the p-lim of a constant is just a constant. So this is going to be equal to beta plus the p-lim of this ratio. So 1 over n times by the sum of the UIXI over 1 over n times by the sum of the x squared. The second rule of p-lims that we're going to use is that the p-lim of a ratio is equal to the ratio of the p-lims, provided the p-lim of the denominator is non-zero. So this is going to be equal to beta plus the p-lim of 1 over n times by the sum of the ux's over the p-lim of 1 over n times by the sum of the x squared. And using the weak law of large numbers, the p-lim of any sample mean is equal to the expected value. So we've got n observations, u1x1 plus u2x2 plus u3x3 plus u4x4 all the way up to unxn, divided by the number of observations, so that is a sample mean on here. The p-lim of any sample mean is equal to the expected value. So we've got the expected value of ux on the numerator, and we've got the expected value of x squared on the denominator. So this gives us that the p-lim of beta hat is equal to beta plus the expected value of ux divided by the expected value of x squared. Now, what does the expected value of ux equal to? Well, in order to find that, we need to use the law of iterated expectations again. So the expected value of ux is equal to the expected value over all possible values of x of the conditional expectation of ux given a particular value of x. If we're given a particular value, we can take that outside of the expectation. So we could take this x outside the expectation. So we have the expectation over all x of x times by the expectation of u given a particular value of x. But this conditional expectation is assumed to be equal to 0, so this whole expression is equal to 0. So this is going to be equal to beta plus 0 over the expectation of x squared, which is just equal to beta. Therefore, our estimator is consistent. 4.5.